Hi guys, Dr. J here. And before we jump into talking about magnetic dipoles, I wanted to refresh our memory on potential fields and different types of potential fields, and then talk about vector and scalar potentials for magnetics. So if you'll recall, we talked about in the last module, I think, the fact that any particular vector field, which obeys certain properties like vanishes at infinity and is continuous, can be expressed as the sum of two potentials. Right? So this is what we had learned before. Any vector field can be expressed as the sum of a scalar potential. Right? So this is a scalar potential. What example have we seen of the scalar potential already? That was our gravity field, of course. So our gravity field is G is equal to the gradient of the gravity potential, or the negative gradient. Again, we've talked about that before. So that's one kind of potential field, but there's another kind here. Whoops. Draw my little swirly brackets properly here. That is called the vector potential. Okay, so in this case, we don't have a field is equal to grad of a potential. We have a field is equal to del cross A. Del cross A is where A is the vector. We call that a vector potential. And A is in fact a vector. So phi here is a scalar field, three-dimensionally varying, but a scalar field. A is a vector valued field. So also three-dimensionally varying, but a vector. So what we're going to talk about now is our magnetic field B. Remember, magnetic field B is a vector. B has a vector potential, del cross A. Del cross A. And in some cases, it may actually also have a scalar potential, but we're going to talk about that in just a second. So let's talk about Maxwell's equations. Maxwell's equations relates the curl of B, del cross B. Remember, what did Maxwell's equations say about the divergence of B? Del dot B is equal to 0. Okay, that's one of Maxwell's equations, and that's even in the presence of sources. So now we have del cross B, and this is not going to equal 0. That was the case for the gravity field, but now we have the magnetic field, and that is going to be equal to 4 pi Cm. Remember Cm, that's what we were using for our magnetic field constant. And then we're going to have a bunch of currents here. So I've got currents from macroscopic currents plus del cross M. M is going to be a magnetization term. Magnetization. That's a long word. So currents related to magnetization. And we'll talk about what this M thing is in more detail later on. And then what's our last term here? These are called displacement currents, where D here is a vector quantity, and we're looking at time rate of change of D, vector currents. Okay, so current density, del cross M. M is magnetization currents, and derivative of D with respect to time. Those are our displacement currents. So these are all the currents, electric currents. Think about these as electric currents. This is what del cross B is equal to. Good. Now let's imagine that we have a region, and I'm going to actually draw this region as kind of a surface. This should be, think of this as a two-dimensional surface. So there's maybe currents coming in, and or field lines coming in and out, and also there may be currents. We can call this IT. The book uses IT for all the currents all together. Okay? So if all the currents, total currents, IT, this is not the word it. Sorry, I didn't draw that very well. But this is just all the currents, total currents. So if all the currents are equal to 0, what does that make this? Del cross B is equal to 0 then. So if and only if, I'll use the mathematics if, all currents are equal to 0, then del cross B equals 0. And if del cross B equals 0, what does that mean? That's the same situation as our gravity, and that means gravity, or there is a scalar potential field. And so what we can do is we can write that then, and this is meaning B is equal to grad V, or negative grad V, where V is some scalar potential field, scalar magnetic potential field. This happens if we are in a situation where we have no currents, if all the currents are 0. There's currents passing through this loop. I've got this loop, and what am I going to call this loop? It's going to have some little increment dl like we talked about. Right, so I'm just going to take the integral of both sides of this, and I'm going to integrate over the surface. I'll need to dot this into the normal, the unit normal. So there's a unit normal to this surface, right? So I'm going to take the integral of both sides of this equation over the surface S. We'll call this S. And again, I need to dot these into the unit normal. So we'll say this whole thing dot n ds dot n ds. And that's going to equal this whole thing, right? So, sorry, I've got kind of a mess now, but we're going to just take both sides of the equation. Del cross B, that's what del cross B equals. This is from Maxwell's equations. We're going to integrate both sides over the some surface. And then what we're going to do is we're going to note that this expression here, del cross B dot n, we can use Stokes' theorem. The Stokes' theorem, this is mentioned in the book. The Stokes' theorem is given in the appendix to the book. So what we're going to do is we're going to rewrite this using Stokes' theorem to be the integral around this loop. So again, we've got an outer edge to this surface. So it's integral around the loop. There's our little line increment. This is also a vector. Taking the dot product there. And that's going to equal still this whole thing. So 4 pi cm, and then I'll just say IT for the total currents, except it's not IT, it's IT dot n. And I need to integrate that over ds, again, over the surface. Okay, here we go. What have we got? The total currents passing through a surface are going to equal the magnetic field, or the magnetic induction flux, or whatever we had called this B, the magnetic field integrated on a line. How does the book say it? The magnetic induction integrated around any closed loop is proportional to the current flow through that loop, the normal component of all the currents passing through the loop. So if we have a loop of wire, and we integrate the magnetic field around that loop of wire, and there's currents flowing through the wire, even if there's no current in the wire itself, if there are currents flowing through the wire, those two things have to be equal. The integral of the field integrated around the wire is going to equal currents flowing through the wire. So we have this relationship here for the magnetic field and between magnetic field and currents. Now, in many geophysical situations, currents are negligible, right? We're measuring the magnetic field out in the air, out in the open, and so we can neglect currents. And so the magnetic field away from those currents, away from any currents, is going to behave as a scalar potential field. B will not equal del cross A, or del cross A is going to equal to 0, but B is going to equal just the negative gradient of some magnetic potential, some scalar magnetic potential V. And this is only valid outside of magnetic media and where line integrals encircle no currents. So again, that's going to be relevant for geophysical applications. It's not going to be as relevant if you're in an engineering context or something like that. So we'll talk more about the geophysical aspects of this as we go along in the next video.